Chapter 13, Buckling Formula Derivation. So let's introduce first a short columns. Let's talk briefly about short columns and long columns. So short columns are those who are controlled by the strength of material and their geometry of cross sections. So short columns are mainly carry compressive loads. They are used in construction. They can handle bending moments about either of their axes, x and y, and they are generally considered as a compression members. So because the compression force is a dominant on short columns, and on the other side, the long columns are those which are a thin and far longer in comparison to the short one, and they are controlled by a term called slenderness. So that's a ratio of length to the radius of gyration. We'll talk about it in details later on. So that was a brief introduction about short and long columns, and let's jump to columns failures, which they are categorized in three main groups of failure of short columns, failure of long columns, and also failure of a middle grounds of them. So that's intermediate columns. So by short columns, we do mean a slenderness is a very low because it just they are very short, and by long columns, the length, effective length over radius of gyration, which is called a slenderness of the column, it just goes high because they are long, and we can say a critical stress in, for example, if the column is from steel, a critical stress is just related to sigma y, yield stress of a steel, and but not to the modulus of elasticity for short columns. Likewise, a critical stress in long columns is just related to the modulus of elasticity of that material. For example, if that's concrete or steel, just replace it by the uh, E of concrete or steel. But it's related to modulus elasticity, but not sigma y. And one can guess sigma critical in the intermediate column is a function of Botham. So sigma y and modulus of elasticity of, again, if that's from a steel, goes by steel, and if that's any other material, just goes by sigma y for example, concrete, brass, whatever you have, and modulus of elasticity likewise for the same material. And if we draw sigma critical stress due to a compressive load versus the slenderness, which is KL over R, which we'll talk about it in that's effective length over radius of gyration. So again, you can see observe a three uh, area, which is short columns, long columns, and in the middle there is intermediate columns. So again, a LE over R is low in short columns. In long columns, it just goes higher because they are long enough. And the first part, short columns are one can say all this part is just you can guess the curve by estimate the behavior of uh, critical stress from the parabola equation. And for long columns, instead, you can just goes by you can go by Euler's formula, which is this curve, and talk about Euler's formula in a second. So again, in short column, sigma y is just a function of sigma y. Critical stress is just a function of yield stress, In long columns, sigma critical stress goes by Euler's formula, and in the middle one, which is a complicated case in comparison to the other two others, that's a function. Critical stress is a function of both of them. Hmm? So let's go to the Europe in 18th century. Mhm. In Switzerland, which a Leonhard Euler, which is a great mathematician in Switzerland in 18th century. He is a Swiss mathematician, physicist, astronomer, geographer, and engineer, which pioneered a lot of interesting topics and discoveries in branch of mainly in mathematics. Mhm. And we want to derivate his equation for bucklings of a columns. So again, this is the equation of Euler's formula for bucklings of columns. We want to derive this equation. Mhm. Let's see how that goes. So we want to know what is Euler's critical load formula derivation. So if we have a column and there is a compressive force applies at with a distance from a, let's call that for example y. So if that load applies to uh, our column with a distance of y from the center line, we can replace that with the force at the center line with a moment created at both ends. You can easily see that's you can translate this effect to a couple and couple and also a axial central force. So, and due to this force, we can have a sagging or a deflection in our column. We want to derive the equation for this buckling. So if we call this point like O, like C, mhm, and we want to derivate the create a moment about point C, summation of moment about point C goes zero, it just gives us a equation for moment at x. Mhm. That's a negative p times y, force times distance. If this distance is y, that's a p times y. And from the chapter 12, which is beams deflection of mechanics of material, we do know EI times y double prime is equal to m equation. Do you remember m over EI was y double prime? And that's y double prime is equal to a moment equation. And that's a negative p times y. And if you just rearrange the equation, you get this one. Mhm. And if we just uh, rearrange it a bit more, we can say and y double prime plus p over ei times y equal to 0. If we just call this term, this constant p over ei lambda squared, so we can write our equation in a far easier approach. So that's a lambda y double prime, mhm, down here, y double prime plus lambda square y is equal to 0. So if you look at this equation, y double prime plus lambda square times y is equal to 0, and that's a linear homogeneous y homogeneous because in differential equation, if you have 0 at the second part, that's a homogeneous. You don't have any function or constant that goes by 0. That's a homogeneous part. And that's a second order because that's y prime, and definitely that's a differential equation. So for solving this equation, if you have a characteristic equation for that, that's a t squared plus lambda squared goes 0. The both roots are plus minus lambda, and that's a p plus minus iq. The general form of answer is a sine of lambda x plus b cosine of lambda x. Mhm. By applying the boundary condition, so for example here at x equal to 0, we don't have any deflection because of a pin here, and also at x equal to L, the whole length of the column, again due to a support, a pin at the end because it's a both a pinned a column that goes 0 again, and by ap applying boundary condition at x equal to 0, y is equal to 0 gives us a first constant goes by 0, so b is 0, and by applying the second part, if at x equal to L, y is also 0, and that gives us a sine of lambda is 0, that's should satisfy lambda times L is equal to n times pi, and that gives us a lambda equal to n times pi over L. So from the previous part, we just defined that lambda squared to be equal to p over ei. So that's lambda is a square root of p over ei. And if we do have lambda is equal to the square root of p over ei from the previous part, and from here we can equalize these two terms with each other. So in that terms, if we just square this equation, it just gives us p over ei is n squared, p squared over l squared. And if you just solve the problem to calculate a force, a compressive force, that's a Euler's critical load, that's a n squared pi squared over l squared, and you just take this ei from denominator to here, that's ei times ei. And at the same time, if you want to know what the smallest n is, that's a critical force. That says critical force of Euler's is just pi squared times E times I over L squared. Mhm. Likewise, if we do know P critical from previous part, that is pi squared times EI over L squared, and we just know R is a radius of gyration and comes from the equation square root of moment of inertia over the area, so I is A times R squared. If we just go by sigma, which is a stress, is force over area. We have force over area, and if we just replace that with I here from down here, we replace I in this equation, and then we can easily cancel out the 1a at the numerator but bump with the other a in denominator and reach to this equation sigma critical. We already have force critical of Euler, and this is a stress critical. Critical stress is pi squared times E over L over R squared. We call this term a slenderness of a column. So if L over R is a slenderness of a column, let's investigate the different boundary condition for beams. So it just says if we have a L over R as a slenderness of a column, we can also have a coefficient times L over L. It just says effective slenderness. That's L effective over R. So how that goes? It just says if you have different a condition. So this is a fix. This is a fix. It just says your effective length is a half of the length. This is a pin. This is fix. So it just goes by zero point 0.7 times original length. If it just goes by a boss pin, it's just like a original length. And if you just have a free end and fixed end, equivalent length is 2 y's of original length. So how that goes? And again, sigma critical is pi squared times E over this time effective length over L in parentheses squared. Let's see how that goes. Again, we get P critical, force critical, which is pi squared times EI over L E squared. We just observe it. And sigma critical is pi squared times E over L E over R squared. Mhm. That's just a derivation from a, this equation is just a simply come from sigma is P over area. So that was the main equation and that's a derivation of that. So if we have the condition that we have a fixed at both ends, the effective length is the half of the original length. So that's the effective length for a both fixed end condition. At the same time, if we have P at the top and we have fixed end at the bottom, so this time LE increased by zero point 0.2 times L original length, that's zero point 0.7 original length. Mhm. And if you have a both pin, you can easily see effective length is identical to or equal to original length. And at the same time, if you have a fixed and free, one is fixed, one other, you can extend it to the other side, and due to symmetry, you can see effective length is equal to twice of original length. So a effective length can vary from something a smaller, a portion, a half of original length to something like twice of that. Mhm. So we'll put it to an example in next video to have a better understanding of what's happening. Thank you.